Hello, Mr. Jones here. Here we're looking at mechanisms, which is everything from Knowledge Organiser number 4. Here's a quick look at the contents of things we're going to cover. You can pause and have a look at this. We're going to jump straight into number 1. So, mechanisms are all about movement. So if we're going to talk about movement, I think we need to know some of the names to describe the different ways in which a product can move. So let's have a look at those. We have linear motion. Linear motion is motion in a straight line. Okay, so like a train. A train travels in a straight line in one direction, that's linear motion. We have rotary motion, which is going round in a circle, like the wheels and the crank of a bike. A bit more complicated, now we have oscillating motion. Oscillating is a swinging motion, like a swing, but also the pendulum of this clock. Last but not least, we have reciprocating motion. This is where it's travelling in a straight line, but forwards and backwards. So like the large grey block you can see then in this animation. It's going up and down in a straight line. That's reciprocating motion. Right, let's just have a look at these examples. So a bullet from a gun, that's travelling in linear motion. We have a sewing machine going up and down, up and down, up and down is reciprocating. The swing is oscillating. And then these cool bike wheels, that's rotary. So, have a think here, and I'll give you a few seconds to think about it. What types of motion can you see here? I can see 3 of those types of motion. I'll give you 10 to 20 seconds to have a think about it. Right, what did I spot? Well, let's have a look at the head. The head is going up and down in a straight line. We've got reciprocating motion. Underneath, the guy turning the handle is using rotary motion. And then if we look at just the arm, the top part of the arm, we've got oscillating motion from the shoulder to the elbow. So you can see if we're designing objects with mechanisms in them, it's very useful to be able to know these words so we can communicate it to someone else. Cool toy, isn't it? Let's move on to levers then. What are levers? Well, levers are simple mechanisms. They create mechanical advantage. They make a job easier for us. So let's think of a lever that you've used. Imagine using a screwdriver to get the lid off a tin of paint. We lever the lid off the tin of paint. Well, that's giving us a mechanical advantage. It's much easier to get the lid off the tin of paint with a screwdriver than it is doing it with our fingers. The mechanical advantage of that might be 20 or 30 times easier than trying to do it with our fingers. So here we go then. Here's a couple of levers. What words do we need to know here? Well, when we're talking about levers, 3 words are really important for us. Effort, fulcrum, and load. Effort. Well, let's zoom in, let's have a look. So here, that's zoomed in a bit close, isn't it? But here for the nutcracker, we've got the effort is squeezing the blue handles with your hand. So as a human, you're putting the effort in. The load, that's the nut. Okay, so the load is what's pushing opposite directions to the effort. All right, that's resisting the effort, and that's the nut. And then the fulcrum, if you've not heard of one of those, it's kind of like the pivot. Okay, the pivot point. So the fulcrum on these nutcrackers is the hinge at the end. That's a nice easy one to do it with. The hammer is a little bit tricky. So we're using a claw hammer to remove a nail. So the effort is in the handle. Okay, we've got the fulcrum then is where the hammer meets the piece of wood that we're rocking it on. And then the load is the nail. So effort, fulcrum, and load. Let's look at those in a bit more detail to help us remember. All right, so the effort, here we can see, is the hand. It's the amount of force being put in by the user. So the input, usually called effort though. We've got the fulcrum, which is the pivot point. So here, it's the middle of the seesaw. And then we've got the load. That's the force exerted by the weight or the nut or whatever we're using our lever for. So that's the output. Now, when it comes to levers, what else do you need to know? Well, there is some maths associated with it, so we can work out mechanical advantage, but we'll revisit that towards the end of the video when we look at how to do the maths. What we do need to know is which of the three classes of levers, any lever that someone might show you, fits into. And by someone, I kind of mean the exam, don't I? Okay, so we have first class levers. All right, so an example of a first class lever are these pliers here. Now, what's the difference in a first, second, and third class lever? It's all to do with the order of the load, fulcrum, and effort. So a first class lever has the fulcrum in the middle. Okay, let's just worry about what's in the middle to help us remember. Because effort and load, well, they'd be the other way around if the pliers were round the other way, wouldn't they? So it's no good memorising what's on the left. We're going to memorise what's in the middle. And for a first class lever, the fulcrum is in the middle. So we can use these pliers to make it easier to cut through or you can hold on tighter to something because of the mechanical advantage. A second class lever has what in the middle? So a second class lever has the load in the middle. And then the fulcrum and effort are either ends. Which ends, again, if we turn the nutcracker around, they'd be on the other side. So it's the load in the middle. And finally, third class levers, you figured it out, it's now the effort that's in the middle. All right, so like these tweezers. All right, imagine tweezing out an eyelash, okay, or a splinter. We've got the load, which is the splinter or the eyelash. We've got the effort where your squeezing is in the middle, and then the fulcrum is where they pivot and join at the other end. A spade is another example of this. So how do we remember that? This is how I remember it. It works well for me. I can remember it every year when I come to have to teach it again. Flea. Okay, so fleas are really strong, but they're small. So I'm thinking flea helps me remember. It's all about like being strong, making things stronger. Okay, so flea. I know flea's got an A on the end. Okay, but F-L-E. All right, 1, 2, 3. So if the fulcrum is in the middle, because F is first, it's a first class lever. Okay, if the load is in the middle, it's second class lever because L is second. And if the effort is in the middle, then it's a third class lever. So dead easy to remember for an exam. Okay, rather than trying to memorize some sort of example. F-L-E. You know what I'm going to say now? Let's just practice it then. What have we got here? Scissors, wheelbarrow, and someone playing with a hockey stick. The hockey stick itself is a lever. Huge mechanical advantage. Because of the length of the stick, I can whack that hockey puck even miles. Puck. It's not the word you want to mispronounce. Okay. Right, so have a think to yourself now. The scissors, what's in the middle? Okay, so the scissors, we've got the fulcrum in the middle. So that's a first class lever. The wheelbarrow, what's in the middle? So the effort is the handles. That's me putting my effort in. The pivot point, the fulcrum, is the wheel. So actually, it's the load in the middle. So a wheelbarrow is a second class lever. And finally, a hockey stick. Now this one is a little bit trickier, isn't it? So the load is the puck at the bottom. Then we've got, what's in the middle? Well, the guy's got his hand and he's swinging with that hand, isn't he? That's the effort. Because I think the fulcrum would be the top hand where he's pivoting it round. If we think about how it moves as it swings in an oscillating motion. So yeah, effort's in the middle. So that's a third class lever. Right, let's move on from levers and to a new word. If we join more than one lever together, it's called a linkage. So here we've got a couple of different linkages. Now linkages can do different things. Okay, they could be used to alter the direction of a movement. So if you put them together right, we can change forward and backwards to up and down motion, or indeed we can reverse it. You can even alter the amount of movement. Okay, think about a seesaw having the fulcrum in the middle. If you were to move that fulcrum either to the left or to the right, that would alter the movement at each end, wouldn't it? Because it's in the middle, if it goes down 1 meter on one side, it goes up a meter on the other side. If you move that fulcrum to one side, a little motion on one side will create a larger motion on the other. So we can use levers and linkages to alter the amount of movement. And if we're altering the amount of movement, you actually alter the force. Okay, so if I want to use a lever to move a heavy lump, okay, I move the fulcrum so the heavy lump only moves a little bit. I, at the other end, move a lot. Okay, I'm moving the lever up and down a lot. That makes it easier for me to lift that heavy object. Now there's a couple of specific linkages the exam board want you to know about. This one here is called a bell crank. Okay, we can see from the green animation there how it works. Okay, if I'm pulling up and down on this bit here, okay, the output motion, so that's my input motion, the output motion is here. So it's reciprocating up and down, but then the output motion is reciprocating right and left. So a bell crank is for altering the direction of movement 90 degrees. Where do we see them? The brakes on your bike. If you've got this sort of brakes on your bike, that's an example of a bell crank. A reverse motion linkage, we mentioned about it reversing the motion. Okay, so what I've got here is as I pull the bottom one this way, okay, the top one is going in the opposite direction. So useful to change motion. And there's an example on the left with a guy going up and down in his lift. Now an exam question, here we go. Explain how you can create a larger output motion from the reverse motion linkages shown. Okay, now how do we do that? How would we get a larger motion out? That's all to do with moving the fulcrum. Okay, if I was to move this fulcrum down here to about here, a little motion here would make a big motion here, big movement here. So you can alter, as we mentioned in the previous slide, the amount of motion by moving the fulcrum. I feel like that's like a primary school science lesson we've just covered there, where you've had to go with levers, I'm sure, at your primary school. Right, let's move on then. Okay, hey, we're back to our cuddly toy. So what we're looking at here is, or are cams. Cams are these red things you can see spinning around. Now, you might think, I've heard of CAM. All right, that's that computer-aided manufacture thing. Well, when you see CAM written with capital letters, C-A-M, computer-aided manufacture, that means the robot's making products for you. When it's lowercase, CAMs, that's these things here. Don't get confused in an exam. It has happened. So let's have a look at them. What are they doing? They're turning rotary motion into the up and down one. What was the up and down one? Yeah, reciprocating motion. So they're really useful for doing that. Now, a couple of key words then we need to look at: rise, fall, and dwell. These describe the motion of the cam follower here. This grey thing that is sitting on top of the cams is called the cam follower. All right, so if we have a look at, for example, let's start with the center one. Okay, this center, the rise is when it goes up. So this one, how would you describe this? Well, it rises and then falls, rises and then falls. Okay, there is no dwell. Dwell is where it stops, but this one's always on the move. If we jump left and have a look at this pear-shaped cam, can you see it rises, it falls, and then it dwells for half a turn? Now that's obviously all to do with the shape of the cam. Rise, fall, dwell. Rise, fall, dwell. Now what's going on the right hand side with this funny shaped one? Okay, it's called a snail shaped cam. So it rises slowly then drops quickly, rises and falls quickly rather. So it rises slowly, falls and then dwells. Rises slowly, falls quickly and dwells. In an exam they might give you a cam. Now these are the three most common shapes, but there are other shapes, and you just have to sit and rotate it around in your head and try and figure out what motion the cam follower would have. Okay, so this guy has selected the appropriate cam. Now which cam has this guy used to make this toy? Now we can't see because we're looking at it from the edge, but let's have a look at the motion of the cam follower. It's going up and down, and there's no stop, so it's this one in the middle. Okay, we need some names. All right, let's just have a look at the names. So obviously we need to memorize these names. So I did mention a couple of them. We've got the pear-shaped cam because it's the shape of a pear. It's more like an egg, isn't it? But it's called a pear. Forget I said egg. Didn't say egg. Never mentioned egg. Now I've said egg more than I've said pear. It's pear. It's a pear-shaped cam. Okay. This arise and fall and then dwell. Okay. We've got this one in the middle. Okay. This is an eccentric cam. Okay. So it's a circle. It's a perfect circle. Now, if the axle was in the middle of a perfect circle, what would happen? Nothing. As it turned, there'd be no movement up and down. Okay. Because it's the distance between the middle of the axle and the edge of the cam that makes it move up and down. So because I've put the axle off center, okay, I'm getting a up and down motion. Okay, so weird name, hardest one to remember, eccentric cam. Okay, quite a hard one to say as well. And then finally, the snail cam, or sometimes it's called a drop cam as well for obvious reasons. Now, in the blue in the bottom corner, it talks about explain the movement of the follower, and we've discussed that. So in an exam you might have to explain the movement, or they might have to say, or they might tell you, right, we want this movement on this machine or toy or whatever. What cam do you think would be most suitable? Right, let's move on. Now let's spend just the last little bit of time looking at cams, looking at the cam follower, the thing that sits on top and moves up and down. Now there are different types of cam follower. Okay, these are not in those sort of toys that we've just been looking at, the turny handle toys, but when we're looking at using them in machines like steam engines and car engines, they have different types of cam followers. So on the left we have one that's a roller, so it's a little wheel on the follower. Now imagine that, a wheel on the follower, rather than just a flat foot that we've looked at before, where perhaps there'll be friction. Okay, where the flat wooden foot was rubbing, it wasn't it, underneath the teddy bear, it was rubbing against the wheel. You might not want that in a machine that's moving really fast. That amount of friction might cause heat and cause a problem. So we've got a roller wheel. So if we're going to use something at high speed and we want no friction, we stick a wheel on the end of it and it moves. Right, and that's a car engine is a great example of where that's used. Okay, that's moving thousands of revolutions a minute. Right, then we've got the knife edge, where it's got a point on it. Why would you want a point on it? Well, putting a point on it means that the movement will be more accurate. Okay, because it's only got a small part touching this. Okay, so it's going to be more accurate. Where do we need those? Something like a sewing machine is where you'd find those, where we need accurate motion for the needle going up and down. And then finally, if you've got quite a lot of friction, okay, and you've got to put a lot of power through the system, you might have a flat follower. The flat follower then sort of spreads the surface area, okay, so it reduces the pressure on any one point. So this is a strong one, but it does increase the friction because you've got more surface area contacting. But it is powerful enough to use in like steam engines, like steam trains. So I've mentioned the word friction a couple of times here. Let's just make sure we understand what friction is. Okay, I am reasonably sure that you do. Okay, so friction is the resistance of movement between two surfaces. So if you put your hands together, I learnt this in primary school, I'm sure you did. Put your hands together, squeeze them hard and try to move them. Okay, it's friction that makes your hands sort of stick together. Okay, now rub your hands frequently over and over again, and they get hot. Okay, imagine if that was a machine running around at many thousands of revolutions per minute. All right, that could get incredibly hot and cause trouble. All right, so friction can be a good thing. Stops us falling over, the friction on the bottom of our feet, on our shoes, to the floor. All right, but in a mechanism, friction is often a problem because it wastes energy and can cause heat. Right, pulleys. I'm sure you've seen one of these as well before. The idea of a couple of wheels held together with like a rubber band. So what is a pulley? A pulley is a way of transmitting motion from one wheel or axle to another one. Okay, the one that's the powered one often has a motor on it, obviously. So that's called the driver, and the one it's turning on the other side of the rubber band is the driven. The rubber band relies on friction. Okay, so we know what that is. So it's using the friction on the wheel when it's spinning around. And what do we need these for? Well, they can transmit motion, but they can also alter the speed and force of that motion. So if I have a large wheel attached to the motor, attached to a small wheel that's 10 times smaller, not only is it 10 times smaller, the driven, but it will spin 10 times faster. For every one turn that the motor turns, my driven wheel would go 10 times, or 10 turns. So there's a ratio between the diameter and then the amount of RPM, revolutions per minute, or turns. Now, because it's a rubber band, if you're putting a lot of power through it and you're trying, we've got them in machines at work, we've got these in our pillar drills. Okay, if we're not careful, if you're trying to drill a large hole in something really hard, the rubber band can slip on the wheels. Okay, so how do we stop it slipping? Well, we make sure the belts are nice and tight, because that increases the friction. So we don't want any slack. It has to be a really nice tight belt. Okay, and we also look at the shape of the belt. We use what's called a V belt. So a V belt, as we can see here, has one or many V's cut into it, and then you'd have the same sort of shape in the metal wheel. So you're increasing the surface area. Okay, rather than just touching across the bottom, it's now touching inside each of the V's. So a larger surface area means more friction, which means less likely to slip. Oh, so, sorry, I can't believe I made that noise. I've watched this like 10 times. Okay, so what else do we use pulleys for? Well, we can use a pulley system to make things lighter to move. So this guy's, I think, he's got it set up maybe with a couple of pulleys. Okay, so he's pulling, maybe, imagine he was pulling his pulley 2 meters and the car was moving up by 1 meter. That 2-to-1 ratio, the car would feel half the weight, okay, when he pulled on it. If you just had one pulley, it would feel the same weight. But if you have 2 pulleys, all right, and you can so you move it 2 meters and the car only moves 1 meter, that car will feel half the weight. So instead of feeling like 50 kilograms, it will feel like 25 kilograms to lift. We'll look a bit more at this later on in the math section. But it's important you understand that pulleys can also be used to lift heavy weights. Okay, cranks and sliders. Okay, so the crank is the round wheel spinning around here. You might know that where the pedals go, where your gears are at the front of your bike, that's what we call the crank that the pedals are attached to. Okay. Then the slider is this thing moving here with reciprocating motion. So a crank and slider turns rotary motion here into reciprocating motion, or vice versa. Where do we find this used? Engines. Let's have a closer look at a car engine. Okay, so let's have a look at this animation first. This is how your car engine works. So we know, obviously, it burns petrol, unless you want those flash electric ones, but let's ignore those for now. If we're burning petrol and diesel, okay, that's what's going on here. There's a little explosion in your car here, and that explosion forces this piston down, okay, which then turns this in rotary motion here, turns the crank in a rotary motion. And this happens many thousands of times a minute, and we end up with this then turning your engine, okay, or turning, and then eventually turning your wheels. So we're using a crank here and a slider to make your car go. So let's just take a second to have a look at the animation here. So you can see inside the engine. So inside your engine, you have a bunch of these cylinders, explosions going off in each, many thousand times a minute. Right, let's move on. Okie dokie, where are we up to? So what we've got here are gears. So the problem with the pulleys we looked at is that slipping of the rubber. So if you're trying to move a lot of force, okay, something with high torque, which we'll come back to, something that needs a lot of torque, a lot of force to turn, then a rubber band isn't going to be good enough. So what we use instead then are gears. Gears can be made of metal, they can be made of, in a clock in your house, they're probably made of just plastic, nylon. But in a heavy piece of machinery, they'd obviously be made of steel. So they're a toothed wheel, basically, that meshes together, and they can be used then to transmit force, but also then to change the amount of force and the amount of speed. Speed and force are directly proportional. So if you speed something up by twice the speed, okay, by having a large driver and a small driven, if you speed something up, you halve the amount of force it has to turn. Right, so yeah, speed it up twice, half the force. Okay, so we've learned what the gears are. These are these things here with the teeth that are meshed and are spinning around. We've got this thing we need to know about what an idler gear is. At the moment here, we've got A and B spinning, but they are spinning in opposite directions, if you noticed. All right. Sometimes we don't want that in a machine. We want the driver and the driven to spin in the same direction. So to solve that problem, we have an idler gear in the middle. Okay, it doesn't affect the speed of anything, but it just makes the driver and driven turn in the same direction. Okay, that's an idler gear. It's idle, it's not got power connected to it or anything, or an output connected to it. Okay, when we've got a bunch of gears put together, that's called a gear train. So the gearbox in your car, in the bottom left you can see a photo of a gearbox from something. It looks like something from a car. When you've got a bunch of gears put together, it's called a gear train. Let's look at some specific type of gears now. So we've got bevel gears here. So have a look at what's happening here. How would you describe this? Well, this bevel gear then is transmitting the force 90 degrees. A bit like a bell crank does it with levers. It's a bevel gear that would do it with gears. Now you probably used one of these. If you use one of these hand drills, they're doing exactly that. So I'm turning the handle, okay, but the drill bit is spinning at 90 degrees to that. So which gear would be larger on one of these drills, the driver or the driven? Okay, well, we want one turn of my handle to equal many turns of the drill bit. That will mean the drill bit can go faster for every one turn. And these drills, for every one turn of my hand, the drill might go 10 times round. So this big red thing is on the other side of it will be a beveled gear, and there'll be a much smaller one attached to this then. So one turn of my handle would be 10 turns of the drill head. So let's just come back to that key word we mentioned earlier about torque. Torque is the measurement of the turning power in a gear. So for example, an engine for a lorry would need more torque than an engine for a little family car. Okay, so it's how much power is being put into the system. So the torque here on this hand drill, how much torque is being put in? Well, that will depend on the person using it. All right, you lot doing your GCSEs, in theory, should be able to put more torque in than a little year 7 kid, because you're providing the torque for this machine, aren't you? Okay, another one we've got is rack and pinions. So what's going on here? Can you see we're turning rotary motion into linear. You could argue it's reciprocating because it's going backwards and forwards, but if you turn it one way, you get linear motion out the other end. So in the workshop, we have a rack and pinion on the back of our pillar drills. As I turn the handle to move the bed up and down where I'm putting my work, the handle is attached to a pinion, which then moves up and down a rack. So where on a car might you find rack and pinion? Where do we need that motion? Right, so yeah, not all cars have this anymore, okay, but rack and pinion steering was once a thing. The idea that the pinion would be attached to the end of the steering column, and then the rack would move left and right, which would then steer the car. Okay, let's have a look at the maths. Now, don't panic. The maths for mechanisms is reasonably simple. You'll be given a formula, and the most you'll have to do with it is rearrange it. Where can you go wrong? You can go wrong in the same in a normal maths question by the units of measurement not being put in your answer, or incorrect if you have to convert them. There isn't a huge amount of converting units of measurement here compared with when we're doing volume and surface area. So as long as you know how to use one of these formula triangle, you'll be okay. So let's just make sure you do. What we're going to look at first then is what's called velocity ratio. So if we're thinking about levers now, we're back onto levers. Okay, what is the velocity ratio? What's the ratio between how far I have to move my hand, the effort, to how far the load moves when I'm trying to lever a big heavy rock? Okay, the effort, I'm going to move loads more at my end, and the rock will only move a little way. Why? Well, if I do that, it will become easier to use. I'll have good mechanical advantage, won't I? So let's feed this velocity ratio into the formula triangle. Could you do it? So yes, what we've got here then, we put the velocity ratio here because velocity ratio equals effort over load. All right, so these two here, remember, you times them together, so these are the divides. All right, so effort over load. So VR, effort over load. So it's even written kind of in the same order, isn't it, here? So you need to practice that. Okay, being able to feed those into there. If you need a little more help, okay, remember that these are divide lines up here, aren't they? And this is a times line because they're next to each other. So if we were going to work out if we needed to know the velocity ratio, that would be effort divided by load. And if we need to work out the load, that would be effort divided by velocity ratio. So I've just told you the answer to that, haven't I? Okay, go on, can you do it? Pause here if you're not sure. Right, so E equals VR and L, so that's VR times L, that's the times line, isn't it? So E equals velocity ratio times load, and load equals E over VR, effort divided by velocity ratio. Cool. I'm sure you can do that. Right. Let's have a go at this. So here we are. We've got a flea. He's joined us from earlier on in the video. And on the left, we've got Mr. Snuffleupagus. So if the flea is going to have a go at lifting Mr. Snuffleupagus, the flea would obviously have to move the lever a lot more than Mr. Snuffleupagus would move to get that mechanical advantage. Fleas are strong, remember, though. So let's work it out here. What's the velocity ratio of this lever? Well, we need to work out the velocity ratio, which is effort over load. Okay, so how much does the effort move? That was the flea. That was going to move a lot. So let's say it moves 200 centimetres. And Mr. Snuffleupagus, he's only going to move a little bit, 20 centimetres. So what would the velocity ratio? What's the ratio between how much this moves to how much this moves? Well, effort over load. So effort is 200. Load is the L of Mr. Snuffleupagus, which is 20. So 200 over 20. You can work that out with your calculator in an exam. is 10. So the velocity ratio here is 10. This flea will move 10 times more than Mr. Snuffleupagus. And Mr. Snuffleupagus will move 10 times less than the flea. Okay, so what I want you to have a go at doing now is filling in the blanks in this chart. Start off by working out a few velocity ratios to prove you can do it, and then rearrange the formula to work out the effort and the load. So I'm going to get you to pause it now because I think you need to prove to yourself that you've kind of understood what's going on. Right, pause now. Right, welcome back. Well, you didn't pause, did you? Okay, so let's just work this out together then. So velocity ratio is E over L, effort over load, so 800 over 100. Well, if we knock the noughts off, that's 8 over 1, which is 8. Okay, another way of doing it is, of course, going, well, 600 over 50. How many 50s in 600? Well, this actually works out quite nicely, doesn't it? Okay, so we know there's 12. And then finally, doing the same here, we can work out the answer is 22. So what about effort? So effort equals velocity ratio times L. So these two numbers times together this time. So 4 times 250 is 1,000. And then we have to work out the load. So load is effort over velocity ratio. So effort divided by velocity ratio. So effort 750 divided by 15 in my head comes out at 50. Right. So in an exam, could you do that? Now, there are a bunch of other formulae we're going to have a look at now, but the process is the same. Stick it into a formula triangle, rearrange it if you need to. So we've looked at velocity ratio. Now let's look at mechanical advantage. I'm going to use the same sort of figures here so we get the same ratio. So mechanical advantage is the load divided by the effort. Okay, so the load here is my heavy Mr. Snuffleupagus, no offence. And then the effort is the super strong flea that we have putting in 200 newtons. So he's putting in 200 newtons and the Mr. Snuffleupagus weighs 200 newtons. So let's do some maths. There you go. I've stuck it into a formula triangle. We've got the numbers here. So the effort from the flea is 20 newtons. Mr. Snuffleupagus weighs 200. So 200 load over 20 newtons equals 10. So the velocity ratio is 10. Sorry, the mechanical advantage rather is 10. Hey, that was right. The velocity ratio was 10 as well. So you notice we're basically working out a ratio. So the velocity ratio would be 10 and the mechanical advantage is 10. Okay. The flea moves 10 times more than Mr. Snuffleupagus, but it's also 10 times easier. The mechanical advantage is 10. It's 10 times easier because of the amount he moves to move it, the 10 times less force needed. So you see, velocity ratio and mechanical advantage kind of go hand in hand. The more you move, the easier you make it, and then vice versa. So, next slide. Now, you might get asked to work out the efficiency of this. So how efficient is this? So for efficiency equals mechanical advantage over velocity ratio, which we've worked it out for this. We've done both, haven't we? So it was 10 and 10 times 100%, sorry, which gives you an answer that this mechanism is 100% efficient. Now, that only works, like, this lever is only 100% efficient in maths. In the real world, it wouldn't be 100% efficient, which would mean that what effort you put in here wouldn't be rewarded by exactly the amount of force on the other side, because in the real world there are things like friction. So we are losing energy to friction. Okay, it's generating a little bit of heat. So no lever will be 100% efficient. A car engine is apparently a petrol car engine is apparently only 7% efficient because all the energy that's lost to friction, heat, sound, I guess, and light even. So in the real world, things aren't 100% efficient. So in the real world, the mechanical advantage, if we worked it out with weight, like pulleys and working out the actual weights that we were lifting up one side, the mechanical advantage wouldn't be 10. The velocity ratio would be 10, that wouldn't change. But the mechanical advantage will be less than 10, which will give us less than 100% here. Okay, so velocity ratio isn't just for levers, we can use it for pulleys as well. So the formula, velocity ratio equals the diameter of the driven pulley, so the one that's being turned, by the diameter of the driver pulley. Okay, we could use the circumference in the two circumferences, but it's easier to work out the diameter by just whacking a tape measure across it. So we use the diameter. It will be the same ratio. So let's just do the maths here. Looking at the diagram, the driven has a diameter of 200 millimeters, and the driver has 600, so 200 over 600, which is 1 over 3. If we work it out, obviously get rid of the noughts, 2 over 6, and then 1 over 3, half them both, which gives us a 1:3 ratio, a velocity ratio. So for every one turn of the large one, the small one, the driven, goes 3 times around. So here we're using the velocity ratio, we're speeding up. So we're taking the motor and we're speeding it up so it's going 3 times as fast. But don't forget, when you do that, then the force there goes 3 times less. So the amount of force this one turns with, or what it can turn, is 3 times less. Right. We can do the same with gears. When we're working out with gears though, we use the amount of teeth. So rather than doing any diameter, we just count the teeth. So the amount of teeth on the driven is 600, and the amount of teeth on the driver is, 600 is 60, sorry, is 30 on the, excuse me, driver. Okay, so 60 over 30 would be, take the noughts off, 6 over 3. So what's the lowest common denominator? So it'd be 2 over 1, won't it? So ratio of 2 to 1. Okay. Right, let's move on. What we've got here is like an epic recap now. So this is everything that's been covered in the video, minus the maths. What I suggest you do is pause the video here and just go through these. What can you remember about each of these? Again, this is worth doing, that repetition. All right, we've done it once, you've heard me talk about it. Have a look at this. Now, if you're struck with something, where do you go for help? Well, you could just load up the knowledge organizer if you think I just need a bit of a reminder, or you could go back and watch that bit of the video again. Up to you. Probably quicker to look at the knowledge organizer. So don't miss this bit. If you didn't pause earlier when we were doing the maths, definitely pause here. I need you to pause and go through these words in your head. Can you remember the 4 types of motion? Can you remember the different linkages we looked at? Okay, can you remember what friction and torque definitions were? The pulleys and gears and the pros and cons of a pulley and a gear. Then for the levers, effort, fulcrum, load, the different classes using flea, practice that. Okay, and then for the cams, have a look at those keywords. Right, pause here. And the only thing on the next slide is me telling you where to go to more revision. Okay, so pause here. Right. So if you need more help, watch the video again. Speak to one of your teachers, or if you want to practice this, if you think you understood everything, but you think I need to practice this at some point in the future, all right, leave it a few days and then jump on the Quizlets. Or there's a Google form test as well for this. Do those a few times. When you're ready, maybe jump on the sample exam questions. Look out for extra maths help if you need it. Okay, this was just a quick whiz through with specifically just for mechanisms. Right, think about how you're going to space your learning out. And thanks for listening. Any problems, any queries, speak to your teacher. Okay, Mr. Jones out.